let's continue on and start talking about coupled differential equations. And so coupled differential equations are effectively when you have multiple differential equations that have each variable in them. And so when we actually were solving the 2D second order ODEs with ODE 45, we were creating coupled differential equations. So a coupled differential equation is like this left one here. And so I'll do this example here in a moment. But this left one has x dot is equal to x plus 5y, and then y is defined in another equation here. Y dot is equal to 2x plus 3y. And so a normal ODE wouldn't have had another variable in the equation, but effectively it's like a system of linear equations. You have more than one variable. And based on how many variables you have, you need to have that many differential equations. And so typically the way you're going to do it is you're going to isolate the derivatives again. You're going to solve them the same way as you did before. So this actually gets solved the same way as before. You solve for the highest order derivative. In this case, it's already done. And then you just set up your equations. And so let me show you. And then I'll talk about this. I probably won't show you this example with these go-to blocks, but because I think I've already talked about them before. I showed them in a previous example. But let me go through this example for you. So let me pull it to the side for now and open a new thing of Simulink. So I'm going to copy and paste these because I don't need this whole thing open. It feels a little too much like cheating in Simulink. Okay. And so I can close this in full screen. So I've got x dot is equal to x plus 5y, and then I've got y is equal to 2x plus 3y. And so I'm going to do this like I did a couple of the other original examples before, is I created some dummy constants that are going to take the place of x and y. And so let me do that first. I'm going to go grab a constant block. I'm going to call this one x. I'm going to right-click and drag and call this one y. And so these are going to be my placeholders for x and y. And so my first equation is going to be x dot is equal to x plus 5y. And so I'm going to need the addition block because I'm adding x plus 5y. And then I need the gain block because I need to multiply y by 5. If I grab that, and I can just now start connecting, and then I'll start labeling my lines like I've done before. And so this is just going to be x. This is going to be y. This is going to be 5y. And then this is x dot. Right? X plus 5y. And now to get x, I integrate. I'm going to grab the integrator block. I need to have an initial condition. I don't think I defined one because I was only worried about the setup. And so I'm just going to say my initial conditions for both x and y are 0. That might mess up my solution. It might not look like anything, but that's fine. And so the output of the integral of x dot is x. And so I need to connect these two, right? So now I have x, and I need to connect them. And so this was a placeholder for when I've calculated x. I've calculated x now. And so now I'm going to feed this back. Because in reality, what this was saying was the integral of x dot is equal to x, and you need to go back and use it in your original equation. I'm just going to remove that label. So this is the first equation. The problem is I haven't defined y yet, and this is why coupled differential equations. I have two equations, and the second one is going to solve for y dot, integrate it for y, and then it's going to plug it into this equation. And so I'm going to start out with this second equation in the same way as before. I have x and I have y. X I can connect to this one, but I'm going to do that in a minute. So now I need to know y dot is equal to 2x plus 3y. I know I'm going to need a couple more of these gains because I need to multiply x by 2 and y by 3. So let's do that first. So x times 2 and y times 3. And then I'm going to need this add block again. Right there. So this one is 2x. This one is 3y. And so this output is 2x plus 3y, but that's also equal to y dot, which I can then integrate again in order to get y. And so now I do the same step as I've done before. I can connect y to y and x to x. So this x I already have, it's connected to right here. So this x goes into there. Cool. Now it's starting to get a little messy, right? Especially now that I need to connect y to these other two. So y goes there, and then y is going to go into the first equation. And I'm going to right-click this line, pull it over, and now I have y connected. And now I can solve this equation. So I can hit play, it ran, and now I can grab a scope and plot, let's say plot x. And again, it might not look like anything because I just kind of made up these equations, but there, it's 0 probably because my initial conditions are 0. But this is the solution to that differential equation. That set of coupled differential equations. So effectively what the next slide was going to talk about is something I've already talked about and I'm going to use on the next examples is now you can see you've got lines running everywhere, right? And so you can imagine if you had, let's say it's a system of 3 differential equations, what lines are going to start getting interconnected and it's going to be hard to follow everything. And so that's what these go-to tags and from tags are for. And so whenever you have something that's going to go to multiple places, you can use a go-to tag and say, all right, you have a tag called X. Every corresponding from tag that has X is basically pulling from that same tag, pulling from that same line. And so in this case, it's like, all right, you go to X, and then X is used in both these equations. These things are the same as if all 3 of these were connected, basically. The go-to transfers a signal to a corresponding from block. And then that's kind of a way you can clean up your code. And this actually looks nicer, right? It's actually like a 1-for-1, those placeholder constants to go-to blocks. And that's how I'm going to represent the next couple examples. I'm going to use these go-tos instead of running lines everywhere. And so now I'm going to solve another set of differential equations. x1 dot is equal to 6x1 plus 4x2. Then x2 dot is equal to 5x1 minus 7x2 plus 3t. And so this is just going to be me going through these same motions again. And so let me pull up a new Simulink canvas in order to make a new model. And so let's do this x1 equation first. And so I'm still going to use these placeholder constants because that's just a good way to visualize things. So this first one's going to be for x1. And the second one is going to be for x2. So x1 isn't red because it's already in my workspace, because that was from the previous video. But ignore that. I'm going to delete those eventually anyway. So now I'm going to need 2 gain blocks, right? Because I need to multiply x1 by -6 and x2 by 4. So let's grab a gain. And this first gain is going to be -6. Then I'm going to right-click drag. The second gain is going to be 4. And now I need an addition block. So I'm going to click off, start typing in add, and then connect everything. And now I can label a bit if I need to. So this is going to be -6 x1 and 4 x2. And then this is equal to x1 dot, the derivative of x1. And now I can use an integrator block in order to now solve for x1. And I don't really have I don't have an initial condition again, so I'm just going to use 0. If I don't give it to you, you just assume it's 0 because that's the baseline for this block. And so this one is equal to x1. And so now I can replace this constant with this actual value that was just calculated of x1, and I'm going to use go-to tags. So let me show you where those are again. If I click on this library browser and I go to signal routing, it's right here. There's a go-to tag right there. And that go-to tag I'm going to call x1. And so let's replace this with a from tag of x1 as well. So this from tag, if I drag that off here and say I want to have this go tag be connected to these from tag connected to the go to tag x1. and connect it. All right, so now I still have x2 missing, so now I need to create my x2 equation. And my x2 equation is just a little bit more complicated, not really that much more. And so I can just copy this x1 down here and copy this x2 down here. And then I'm going to need a clock because I have 3t in my equation. So let me grab a clock. And now I need 3 gains because I need to multiply x1 by 5, x2 by -7, and t by 3. So let's grab this one, and I'm just going to connect them. I'm just using the auto connect function when I can. So the first one, x1 is multiplied by 5, x2 is multiplied by -7, and t is multiplied by 3. And now I need another addition block. And so in this case, I need one that has plus, plus, plus. And I don't need a minus because I've already included the -7, the subtraction sign, into the -7 gain. So I don't need to subtract by 7 in this case. And if you've noticed it, they all kind of retrieve the same naming convention as was up here. I'm just going to call this one 5x1 -7x2 3t. I need to get rid of this -5. And again, this stuff isn't necessary, this labeling. It just helps me and hopefully helps you follow me a little bit better. It's kind of my other goal. And so my output here is now x2 dot, right? Because my x2 dot is equal to 5x1 minus 7x2 plus 3t. And so now I can right-click, drag, copy this, paste it. And now my output is x2. And so now I'm going to create a new goTo tag that's going to stand for x2 and grab froms for these x2 values. So I'm going to grab a goTo. This goTo tag is going to be called x2. I'm going to connect it here, and then I'm going to use this other shortcut that I showed you in one of the last videos. And you see this little arrow pops out to the side? If you highlight that, it gets a little bit bigger, and you can click on it and drag, and it creates a from tag for that corresponding goTo tag. And so that is going to go in place of all of these x2s. So that one's going to go right here. Then I'm going to right-click, drag the copy, and put it right here. And so now I have solved my equations. And so now I'm going to plot x1. So let me grab a scope. I have this right here. I might as well grab it. Sync, grab a scope here, and I'm just going to plot x1. That'll be my solution. All right, and here is the answer to that, the solution to these equations. As you notice, it actually kind of turns into a line. And that's and the reason in differential equation terms is these are pretty simple linear equations. So there's like some time constant here, but this ends up being my forcing function, 3t right there. And so it makes a lot of sense that my response becomes linear because my forcing function, the function that kind of overrides everything else as everything else goes to 0, is the 3t. And so it's not actually 3t, it's a little bit different than that, but it ends up being some line, which is kind of forced by this 3t. And that makes a lot of sense. That solution, that it becomes just a straight line eventually, makes a lot of sense. So it starts out at 0 because those are my initial conditions, and then eventually turns into a line. And so there's the answer to that example. And there's that. And so I'm going to do one last example before I give you your next in-class problem, and this is going to be a more complicated one. And as I said, these just kind of start to get a little bit more and more complicated as we go. And so I want to create a Simulink model to plot the solution to these 3 sets of equations instead of just 2. And as I said, this forcing function that has t in it, these two are going to fight each other now. And so I'm actually kind of curious on what the solution is going to look like. And so I have a solution for x1 dot, x2 dot, and x3 dot. So let's go ahead and do that example. And it works I'm just going to tell you, it works the exact same way as these examples did. Nothing really changes. And so now I don't need to start with these constants. I'm just going to start with the from tags. So wherever there's an x1, I'm gonna use a from tag for x1. Wherever there's an x2 or x3, I'm gonna use a from tag of those corresponding values. So let's just start by using that because I don't want to have to replace them later. getting a little more efficient. I've shown you some examples, so hopefully you're able to follow this now. So this first one is going to be x2. And it's giving me this yellow because there's an matching go-to block because I haven't created it yet. But that's fine. And so I'm going to need a gain of -1, or this time I'll use the add block probably. I won't use a gain of -1. And let me drag another one out, copy it, and the next one's going to be x3. Again, it's yellow because there's no go-to to match these from blocks. I'm going to fix that eventually. That's my goal. And so now I'm going to grab an add block and one gain block for x3. There. This one's going to be multiplied by 2. And then I need to subtract x2 because there's a -1 on it. And again, like in the last example, I could have just added a gain of -1, but there's no reason to. This uses one less block. So that's x2. This one is 2x3. Then the output of this is x1 dot. And now I can integrate it to get x1. Now I can grab a go-to block and define x1. My x1 value is whatever the solution to this equation is. So let me just label this x1, and now I can use x1 in all the rest of my equations without them being highlighted yellow because I've already defined it. So now let's go to the x2 dot equation. So I'm just going to work my way through these 3 equations like I've done in the previous examples. And so I know I'm going to need an x1. So the easiest way to get that is I can actually hover over here like I did in the last example and grab it. And now I have a from block for x1. And I'm going to need x3. And then I'm going to need t, so I'm going to need the clock. And actually, I'm going to need it in a couple places. So what I'm going to do with this clock is I'm just going to send it to a go-to that's going to be labeled t. I'm going to change it. So it's freaking out on me because I'm using the same go-to tag. So this one's going to be called t. All right, so now the clock is going to t. And so I'm going to need x1, x3, and I'm going to need t. And the reason I did that, I created that go-to block, is because I know I'm going to need it in at least 2 places. So this will cut down on the amount of lines that are running around. And I think I used the term in the slide, spaghetti code is what people that use Simulink a lot call it, is because you eventually just get lines that are crossing all over each other like spaghetti. It just doesn't look like anything other than a bunch of lines everywhere. And that's kind of what you want to avoid. You want people to be able to see what's happening in your Simulink models from a high level. Like just looking at it, all right, I kind of know what's going on. All right, so now I need to set up my x2 equation. It's going to be x1 minus 3x3 plus 3t. So I'm going to need 2 gains right here. And I'm going to need this add block again. And so the signs I'm going to use are positive minus positive. Positive minus positive. And so my output of x3 so needs to be times 3x3. This one is 3x3. This one is x1. As this one was x2, but I didn't really feel the need to copy it to label it there. And then plus 3t. And this output is now x2 dot. So now I can use a go-to tag for x2. All right, so now that I've created that, if you've noticed, my x2 is no longer covered in, is no longer surrounded by yellow, giving me a warning, and this one is no longer surrounded by red. Oh, I messed it up. So I created this. I need to actually integrate. So let me drag this over here. And here's the kind of trick that with my error, I can show you something cool. If you just have one input, one output, you can actually drag this block over this line, and it kind of figures out that you want it to be in, you want the left side, you want it to kind of be interrupting that line. And so this is going to be x2. And my initial conditions, I'm just going to call 0 still for all 3 of my values. So that's the second equation. Now, as you can see, my x3 is still highlighted in yellow, so I need to create my x3 equation. And so now I can just kind of, I could actually just copy and paste some stuff. So let me grab my x1 down here, grab my x2, and grab my t. Because those are the three variables that make up x3 dot. And so now I need to grab the gain. So because x1 is multiplied by 2, so it's 2x1 plus 3x2, 3x2 plus e to the negative t. So now I need to multiply this by -1. So to get e to the negative t, I need to multiply this by -1 to make it negative t right here. And now I need to do e to the negative t. And the way I'm going to off here and grab the math function block. And the default is e to the u. So now if I feed negative t into the math function, e to the x, which is defined here as the exponential function, then this is now going to be exp of negative t. And now I can go and add all three of these together. So let me click off, type in add, grab the add block. I know my list of signs, there are 3. I'll just type it in here, plus, because I'm adding them all together. And now I can connect everything. Delete, connect, connect. All right, so I've got all of that now. And now I just need an integrator block because this is equal to x3 dot. And so let me grab the integrator block, connect it. And now my output is x3. And so now I'm finally ready to add my last go-to block for x3, which will just finally solve these equations. So this is the solution. So I want to plot x3. This is going to be my solution. So let me grab a scope. Connect it here. I could plot all of them. I could have changed the amount of input ports here. I just want to show you one of them. I'm going to plot it from 0 to 2 seconds. So I'm going to change my end time to 2 and hit run. And so there is my answer for x3. It starts at 0 because my initial condition is 0, and then kind of follows this odd curve. And so it's hard to understand what the point of this curve is, but just know that it's created based on the forcing functions of these two, and then also these coefficients kind of add parts of these relationships on how fast you basically get to those forcing functions. And so that's how you do that. And so what I want you to do is take some time and do the next problem. Construct this Simulink model to plot the solution to these two equations for 0 to 20 years. These are population kind of solutions. These are two equations that represent the populations of two different, you could say, competing structures, animals, whatever you want to call it. And these are the initial populations of those. So go ahead and take some time to do that and submit those as your next in-class problem.